In lesson 4, we are going to spend time looking at the details of a concept called impulse. To understand impulse, I'm going to use diagrams to illustrate the motion of a tennis ball. Suppose that we have a tennis ball that is moving towards a wall, is moving horizontally towards a wall, and it has some velocity v. The first situation that we're going to look at is that as the ball approaches the wall, is that when the ball approaches the wall, is closer to the wall. So this would be a situation where our tennis ball is just close to the wall, that is just before it hits the wall. In this situation, we are going to start to measure our time. That means here we are going to have initial time, Ti. And you have to notice that in this first scenario, the force here, I'm going to call it F1, is going to be 0 newtons because the ball is not in contact with the wall. The collision hasn't started yet. In the second scenario, the ball will begin to collide with the wall. It will start touching the wall. At this stage, we are going to then experience an increase in the force because the wall will start pushing the ball with a force, let's say F2. And our time, remember that we are measuring, will continue to increase at this stage because we started measuring our time here. So the time will be increasing when the ball continues to collide with the wall and we start seeing a force emerging from 0 to F2. Now you would see that the ball will continue to be in contact with the wall such that the force will also increase further. The force that the wall exert on the ball will increase further, giving us the force F3. It's pushing harder on the ball. And our time will continue increasing as we are measuring it. Now this collision will continue to a point where the ball is completely in contact. It even maybe deforms a little bit because it's pushing harder now on the wall. This means the wall will exert here the largest force, right? The maximum force on the ball. We'll start seeing the maximum force being exerted on the ball. Now the time reading will continue increasing at this part of the motion. At this stage, after we reach the maximum force, the ball will be less in contact, meaning this force is now good enough to start pushing the ball away. The ball will be a bit less in contact with the wall. What that means is that the force will decrease a little bit. Again, the force that we experience from the wall will decrease a little bit. I'll call this F4. It will decrease a little bit, right? Because here we reached our maximum force where they are completely in contact. Now the time will continue increasing again because the motion that we're studying is still occurring. The collision is still occurring. The collision between the wall and the ball is still occurring. Now the next stage of this motion would be that when the ball detaches a little bit from the wall because it's been pushed, remember, to the opposite direction by the wall. So the force here will decrease and become a small force. It will decrease to be smaller than the previous scenario, right? Then we're going to have F5 here. The last part of this motion would be now when the ball moves backwards, it goes to the opposite direction that it came from. So the ball would now be completely away from the wall. It's not in contact anymore. And in fact, it is now moving in the opposite direction with a velocity v. Let me call this initial velocity and call that final velocity with the final velocity, right? So this force was acting on the ball throughout all these different cases until the ball was pushed away. What we observe here, okay, before we talk about this observation, the time will continue until the ball is not in contact anymore with the wall. That means here we're going to have the final time there. So the time period that it takes for the ball to be in contact with the wall will be defined by changing t, which is equals to t final minus t initial. Now, what we observe from this situation is that the force is changing. It started being 0, then increased, and it reached the maximum, started decreasing, and it was completely 0 here. We don't have a force. If you look at this situation here, we don't have a force. Let's say we call this F6 is going to be 0 Newton because the ball is not in contact with the wall anymore. We then call this or say that the force varies with time. The force changes as time increases. It's changing. We don't have a constant force, right? This force is not constant. It's a varying force, right? Now, we can illustrate this using perhaps a graph to say that we have a force here versus the time, right? Now, in this axis, we're going to put time, and in this axis, we're going to put the different forces that we have. And obviously, both of them are measured from 0. The motion will begin somewhere here at t initial. Because remember, when the ball was here, the ball began moving here, going to that direction, right? And we started measuring the time somewhere here when it was closer to the wall. But the force was 0. So the force increased from 0, and then it went to some maximum number, and then it came down again, right, until time t final, right? So the time t final where it was away from the wall. Now, this would mean that we're saying here that at t initial, which is here, our force is 0. And at some time here, which is this scenario here, our force has increased and we get F1. In the next scenario, the time has increased so that we are now at F3 here. When the time continues increasing, we then are at the point where this time has increased and we get the maximum force here, F max. Then as the time continues to increase, we then have a force. The force decreases because it comes from the maximum. It gets smaller. We are now here at F4. Then as the time goes on, that force continue to decrease. It's getting smaller. We are now here at F5. Then eventually the ball has changed direction. It's not in contact anymore with the wall. Then we measure here the T final. That's the T final, and the force is 0. That's why we say in the force it's varying. It's increasing as the time goes on until it reaches the maximum, and it then decreases again to the 0 newtons. So it's a varying force, the force that is changing, but it's changing with time. It changes with time. As the time goes on, it also changes. So it means these two concepts, the force and the time, are important in explaining how the motion of the ball will change. Because remember, the initial motion that we had is that the ball was going to that direction. And we know from Newton's first law that this motion will continue being like this. It will continue moving like this. But it will only change when there's a net force acting on it, and the wall is actually doing that. It exerts a force that is increasing over a period of time until it changes that motion where the ball is now going in that direction. Because the force is changing, we can look at the graph and find the average force so that we can use the average force to do calculations or to create an equation. That means if I take an average force, a force here, I read a force here, right? It will be an average force. Remember, average would be a number that is in between. It's a number that is in between these forces that are increasing and the forces that are decreasing. So this force is the one that is in the middle of them, is an average force. Because that average force is a combination of all these forces that are acting on this object, by definition, it must be the net force. We call that force the net force. Now, we're going to use the net force and the time during which the force acts to then define the change in motion that occurs on this ball. And to actually define that effect, we call it impulse. Is a concept that explains how this ball actually changed its motion from initial to final, where it was going to the right and now going to the left. We then say if we multiply the two, if we take the net force, which is the average of the varying force, times the time, this should give us an impulse. We call that an impulse. So impulse really is the product of the force and the time during which this force is the time during which the force is applied on the ball. And from this formula, we can see that the impulse I is directly proportional to the net force. This is to say that when the net force increases, the impulse will also increase. When the net force decreases, the impulse will also decrease. And also, the impulse will be a vector quantity because it depends on the net force, which is a vector quantity. That would mean that these two are always in the same direction. And again, the impulse is directly proportional to the time. That means that if it takes long for the ball to be in contact with the wall, we're going to have a bigger impulse. If it takes a short time for the ball to be in contact with the wall, we're going to have a small impulse. The SI unit of impulse can be derived directly from the formula. How do I mean? If we use the formula that says impulse is equals to the net force times the time during which this force is applied, we can see that the force is measured in newtons. So we're going to have newtons here, and we multiply that to the time, which is measured in seconds. Now, this is to say now that the SI unit of impulse is Newton seconds. However, we can rewrite the Newton in terms of kilogram meters per second squared. And we still have the second there. Simplifying this will give us a kilogram meters. Now, the second and the second are multiplying each other and they have the same base of s. I'll keep the base from my laws of exponents. And then I'll add the exponents. Remember, there is an invisible 1 here. So that now I have minus 2 plus a 1. And this will give me an SI unit of kilogram meters per second. Now, this suggests that momentum can be classified by 2 units. In other words, we are saying here that 1 Newton second is exactly the same as 1 kilogram meters per second. Because this is the SI unit that comes directly from the formula. But now this breakdown actually comes when we simplify. We break down the kilogram meters per second. Then we end up with a situation where we're saying impulse has 2 SI units, the Newton second and the kilogram meters per second. But there's something very interesting here that we have to think about. This SI unit, we've seen it before, is the SI unit of momentum or change in momentum. Why is that the case? We will provide an answer in the next lesson.